Welcome to the Deep Dive. Today, we're plunging into one of the really big mysteries in cosmology. It's this whole thing about the universe expanding. We've known that for ages, but the really weird part,
It's speeding up.
yeah, accelerating. And for decades, the standard answer has been, well, something called dark energy.
Right. Which is basically a huge question mark. We know something is causing it, but we don't know what. It's this enormous chunk of the universe, supposedly yet totally invisible and mysterious.
Exactly, like a cosmic placeholder. Elegant, maybe, but still kind of admits we're stuck. But what if the answer isn't some unknown stuff? What if it's woven into space-time itself?
Now you're getting to the core of this new idea.
Yeah, there's this recent paper, Evrensel Genişleme, Boyutsal Bir Dalga Kurama by TURÖZ Demiralp. And it suggests, well, a totally different way to look at cosmic expansion. It might even solve the dark energy puzzle by saying space-time isn't just the stage, it's actually part of the action. Dynamic.
That's a great way to put it. It reframes the whole problem.
So our mission today is to really explore this alternative view. The idea that expansion and the acceleration isn't about some mystery ingredient. Instead, it could be an intrinsic three-dimensional wave, like in the fabric of space itself.
Embedded within it, yeah.
Get ready, because this could really shift how we think about fundamental stuff like Hubble's law and, yeah, dark energy itself. It's potentially a major rethink. Okay, so let's set the scene a bit more. This whole acceleration thing. It's like trying to figure out why your car is speeding up when, 70% of what's in the tank is totally unknown.
That's a pretty good analogy, actually. That's roughly the situation in cosmology.
So what is the standard story? The reigning explanation for this cosmic acceleration? And, well, why isn't everyone just happy with it?
Right. So the standard model is called lambda CDNDM. It's incredibly successful in many ways. It uses Einstein's equations, describes how the universe evolves, galaxy formation, the background radiation from the Big Bang.
The cosmic microwave background, yeah.
Exactly. The CMB, it nails a lot of that. But, and it's a big but, to explain why distant galaxies aren't just moving away, but moving away faster and faster over time, well, the model needs this extra component. That's the lambda part, often representing dark energy.
And it's a huge component, right, like most of the universe.
Yeah, the estimates are around 70% of the total energy density of the universe, 70%. And yet, we have no direct detection, no clear idea of its properties, its origin, nothing concrete.
So it feels tacked on.
For many physicists, yes. It feels less like a discovery and more like, well, fudging the numbers to fit what we see. We've labeled our ignorance dark energy.
It's a point of contention, then.
Definitely.
Yeah.
Especially because the most obvious candidate, the energy of empty space itself, vacuum energy. Quantum theory predicts a value for that, which is just absurd, astronomically larger than what we observe.
Like orders of magnitude off.
Orders and orders, yeah. It's called the cosmological constant problem, one of the biggest headaches in physics. Other ideas, like quintessence, propose new fields, but again, no direct evidence.
So the frustration is understandable. It's an ad hoc fix without a deeper theory telling us why it should be there.
Precisely.
Yeah.
It works in the equations, but the physical reality is missing.
Okay, so against that backdrop, let's dive into this paper's alternative. It proposes, what was it? An intrinsic three-dimensional dilatation wave of space-time. That sounds complicated. What does it actually mean?
It does sound like a mouthful, but the core idea is quite different from ways we usually think about. Like light waves or gravitational waves travel through space, right?
Yeah, like ripples on a pond.
Exactly. This dilatation wave isn't like that. It's not something moving in space. It's the idea that space itself, the very fabric, is undergoing a uniform volumetric expansion. Like the whole pond isn't getting ripples, but the water itself is intrinsically swelling up everywhere at once.
Okay. So it's not being pushed from outside. It's inherent.
Inherent, yes. It's described as an isotropic volumetric wave mode. Isotropic meaning it happens the same in all directions. Volumetric meaning it affects the volume of space itself.
Wow. So expansion isn't something happening to space, it's something space is doing.
That's the fundamental shift in perspective, yeah. It's a dynamic property of space, not an external force.
Okay, that's a big conceptual leap. Does this intrinsic waving, does it affect other things we usually think of as fixed properties of space, like its geometry or curvature? Or is it just about the stretching?
That's a really sharp question. The paper mainly focuses on explaining the expansion and the acceleration. But, if you start thinking of space-time itself as this active waving medium, it definitely hints that other properties, maybe even curvature, could be part of a larger dynamic picture. It suggests geometry might be less static than we usually assume.
Interesting.
But for now, the main goal is tackling expansion. And that brings us straight to, well, Hubble's law.
Right. Hubble's law, V. The idea that the further away a galaxy is, the faster it's moving away from us. It's like cosmology 101.
Absolutely fundamental.
And we have a pretty good number for that constant, h, the Hubble constant. Around 70 kilometers per second per megaparsec.
How does this wave theory handle something so foundational? Does it just pop out, or?
This is where it gets really elegant, actually. In this TURÖZ theory, Hubble's law isn't just some empirical fact we observe and then plug into equations. It actually emerges as a natural result of this isotropic volumetric wave.
It emerges from it how?
The theory models the recession velocity, how fast things move away, as vxt, htx, just like Hubble's law. But h can change with time t. And the key thing is the divergence of this velocity field, like how much the flow is spreading out. That divergence mathematically works out to be 3ht, and 3ht is precisely the definition of the overall volumetric expansion rate of the universe.
Whoa, hang on. So the observation that things fly apart faster if they're further away, that mathematical relationship, it's actually baked into the description of space itself doing this wave thing.
Exactly. It's not just observed, it's a direct consequence, an intrinsic property of this waving spacetime. Okay, that is a powerful simplification. It turns a law into a consequence. That's pretty neat.
It is. It provides a potential physical underpinning for why Hubble's law holds.
So if it handles Hubble's law that elegantly, what about the really tough nut to crack? The accelerated expansion. The thing that currently makes us invoke dark energy. How does the wave model explain that? This has to be the crucial test.
It absolutely is. This is the core challenge the theory aims to meet. So the approach starts by defining what they call a dilatation function.
Okay.
You can think of dt as sort of the total amount of volumetric stretching spacetime has undergone up to time t.
Yeah.
Like a running total of the expansion.
Right.
And this dt is directly linked to the scale factor, Betty, which is the standard cosmological measure of how distances stretch. The relation is at, EDAT3. It connects the volume change to the linear stretching we observe.
Okay, standard stuff so far. Connecting volume and distance.
Right. And then the Hubble parameter, ht, which tells us the expansion rate at time t, is just 1/3 of the rate of change of this total dilatation. So ht equals 13 at. The dot means rate of change.
Okay, h is related to how fast d is changing. Makes sense.
Now here comes the dynamics.
Right.
How does this wave, represented by dt, actually behave over time? The theory proposes a dynamic equation. It looks like this. ev plus h plus ad equals sx.
Okay. Break that down for us. Lots of symbols there.
Let's not get bogged down in the math symbols. Think about the concepts. It's like an equation for any wave or oscillator, really.
Yeah.
AD double dot is the acceleration of the dilatation. How fast is the expansion rate itself changing?
Right, the acceleration term.
AD dot represents damping. Think of it like friction or resistance acting against the expansion. Is the damping coefficient.
Okay, something slowing it down, potentially.
AD, omega squared d, is like the restoring force related to the wave's natural frequency pay. It's an intrinsic property of this space-time wave mode, like natural swing of a pendulum.
An inherent rhythm.
Exactly. And then the right side, this is crucial. This is the driving term. It's the source powering the wave, making the universe expand volumetrically.
And this isn't dark energy.
Critically, no. The paper is clear. ST is the fundamental source of the wave itself. It is not vacuum energy. It is not some separate dark energy field. It's the engine driving the space-time wave.
Wow. Okay. So how does that explain acceleration?
Well, the condition for the universe's expansion to accelerate for a double dot, the scale factor's acceleration, to be positive translates into a condition on d and its derivatives. Specifically, s needs to be greater than 0. The key insight is that the dynamics described by that wave equation, s plus st, can naturally satisfy this condition under certain circumstances, when the interplay between the driving term s, the natural frequency s, and the damping lead to 13 plus 19.
Then the universe accelerates.
Exactly. The model naturally mimics the effect we call dark energy. The acceleration isn't caused by adding a mysterious substance. It's an emergent behavior of the space-time wave itself, driven by its own source term.
So, wait, dark energy in this picture isn't a thing at all. It's just what the wave does on large scales.
That's the essence of it. It's reinterpreting the phenomenon. What we've been calling dark energy could just be the phenomenological effect of this intrinsic three-dimensional space-time wave playing out over cosmic time.
That is a fundamentally different way to think about it. Instead of adding an ingredient, you're changing the recipe for space-time itself.
Precisely. It shifts the focus from finding a substance to understanding the dynamics of space-time.
Okay, but a new theory, however elegant, needs to match reality. You mentioned it handles Hubble's law. What about other big cosmological observations? Does it hold up?
Critical question. The paper argues for consistency on several key fronts. First, isotropy. The universe looks the same in all directions on large scale.
Right, that's a big one.
Since this wave is proposed to be an intrinsic uniform property of all space, happening everywhere equally, it naturally explains this observed isotropy. There's no special center, no preferred direction, it just fits.
Okay, that makes sense. What about the CMB, the cosmic microwave background? It's incredibly uniform.
Yeah, the smoothness of the CMB is a huge constraint. This model works well here too because a globally isotropic wave, this uniform volumetric pulsing, wouldn't create large-scale bumps or wrinkles in isotropies that would contradict the CMB observations. It naturally produces a smooth expansion.
So it aligns with the smoothness we see.
Good.
What about the more detailed stuff, like baryon acoustic oscillations, BAO, and type Ia supernovae?
Right, BAO and supernovae. These are our best standard rulers and standard candles. They give us really precise measurements of how the expansion rate, h, has changed over cosmic history as a function of redshift z. So h,
This is where the rubber meets the road, quantitatively.
exactly. The theory, with its dynamic equation for dt, makes predictions for how Hertz should behave. The paper acknowledges that the next crucial step is detailed numerical fitting. You need to take the observational data for Hertz from BAO and supernovae and see if you can find parameters for the wave equation, like the delay and the form of sin t, that actually match the data accurately.
So it makes testable predictions. It's not just hand-waving.
Absolutely. It's computationally intensive work, but it's a clear path forward for validation. Matching those curves would be very strong evidence.
That's really exciting. It means this isn't just a philosophical idea. It's something we can actually test against hard data. It offers a genuinely different framework from Lambda CDM, but one that seems consistent with the basics and is ready for, well, confrontation with detailed observations.
That's right. The paper explicitly mentions this future work, the Hertz fitting, also checking consistency with the specific BAO scale and comparing predictions for how structures like galaxy clusters grow over time against observations. These are all standard cosmological tests.
So we've taken quite a journey today into this really bold idea that the universe isn't expanding because of some mysterious dark energy pushing it apart, but instead it's space-time itself, its very fabric doing this intrinsic waving, an isotropic three-dimensional dilatation wave.
And within that framework, Hubble's law isn't just an observation, it's a direct result of that wave's behavior.
And dark energy. Well, it gets demoted, it's not a separate thing anymore, but maybe just the observable effect, the outward sign of this wave's long-term dynamics. The wave's own song, you called it earlier.
A phenomenological effect, yeah.
So hopefully this deep dive has given you a map, a shortcut maybe, into understanding a really cutting-edge area of cosmology. It's a fantastic example of how science works, right? Re-examining assumptions, proposing alternatives.
Definitely. It shows that even well-established models aren't sacred. New interpretations can emerge and potentially offer new insights.
It really makes you think. Even our most basic ideas about space and time can be challenged.
And that leads to a final thought, something for you to consider. If something as fundamental as cosmic expansion and acceleration could be explained not by adding a new substance, but by seeing space-time itself as dynamic, as this waving medium, what other deep properties of the universe might we eventually understand differently? Could things we currently see as static components or separate forces actually be emergent properties of some underlying dynamic processes of space-time itself?
Like reality is less like a fixed stage and more like a constantly unfolding performance.
Perhaps. Could space-time be far more active, more self-organizing, maybe even more alive in a physical sense than we currently imagine? And if so, how does that change how we search for its origins and how we picture its ultimate fate? It makes you wonder, doesn't it?